Hey guys, we're gonna go ahead and get started. Thank you for joining us today. Just to give you guys a quick introduction, I have Barak here with me, who is the CEO of VIAS. I also have Arindam Chakraborty, who is the Vice President of Advanced Engineering at VIAS. This webinar will be about 45 minutes, and at the end, we're gonna have a 10 to 15 minutes Q&A session. If you guys have any questions at the end, feel free to ask us. And I'm gonna give control to Barak here, and he'll get started with the presentation.
So thank you, Kanis, for the introduction. So this is a series of webinars that we'll be executing throughout this year and as we go next year as well. And we'll let you all know what are the topics that we'll be presenting. We choose the additive manufacturing as one of the first topics because a lot of manufacturing companies, they're actually looking into how the AM can actually enable their processes and how it can enhance. So we are going to talk about the topic as we progress. So what I'll do is a quick brief introduction about VIAS. If you have any questions, please reach out to Susan, your sales executive. And any technical topic, you can reach out to me and Arindam. For PLM related, either implementation or support related questions, please reach out to Kevin. So I'd like to take this opportunity to thank all of you for your business, and we just wanted to reiterate that with the Idex PLM business acquisition, we just enhanced the existing capabilities. In addition to CATIA design capabilities, you have an access to the rest of the portfolio, from the simulations to digital manufacturing and the NOV implementation side. So we like to continue adding value, enable your teams with those solutions. So as VIAS, we are one of the few PLM Platinum Partner and providing software solutions with CATIA, Simulia, Delmi, and Novia, and as well with the 3D Experience solution. We have presence in Houston, Chicago, Cincinnati, Portland, New York, Toronto, and Sacramento. And we are continuously growing both our sales and support and engineering team as we grow. And we'll keep you updated on the changes within the organization as we grow. As part of our technical services and software solutions, we have resources, not only have a product knowledge, but having working experience at different industries. So we can provide not only the value or the information from that experience, that industry, but we can always bring the cross-industry, the value or some of the solutions to your specific industries. So we have resources in aerospace and defense, automotive, energy process utilities, nuclear, marine and offshore, industrial equipment, medical devices, and high tech. In addition to our software solutions, we also provide, so we enable our customers through the training, and if it requires a customization and automation and workflow development, we can enable on the workflow development. And if it requires any additional resources, we can always enhance your technical team through our engineering consultancy services. So we have a strong technical team with many PhDs and master's degrees in design, manufacturing, solid mechanics, robotics, and fracture, composites, multi-physics applications, thermal and fluid materials and corrosions, optimization and reliability, data analytics, and system and hardware architecture, where we can enable your team with our key resources. In addition, we can also help either with the additive manufacturing simulation, as well as with the 3D printing services. So what we can offer to our customers, in addition to, we can provide pretty much a software solution for the entire portfolio, but we can also enable your companies through the implementation services for the Dassault Systems product. In addition, we have a strong technical team where we can provide a technical support either with the implementation, installation, or product-related question. And also we can train you on those products, either on site at your facilities, or we can enable you through the web training enablements, or we can host you at our facilities. In addition, we can also provide the design and advanced simulation capabilities to enhance your capabilities. What we can help you with the implementation services before you are implementing the software configuration. We can look at your business processes and do the analysis, and offer you a process where we can actually optimize your product development. In addition, we can develop what are the best practices and working standards, which is most suitable to your organization. And then we can configure and customize the right software solutions for your needs. And we can customize some of those, the software solutions based on the knowledge within the company. We can maintain and automate, and we can enhance your product development activities. And we can provide the training and methodology development. And we have the project management activities where we can manage and make sure that we stay within the schedule, and also with the budget that we define when we start the project. For the design side of it is, in addition to general CATIA design activities, we also have some specialist capabilities where our resources have significant industry expertise in composites, machining, electrical, fluid systems, function-driven generative design. In addition, we can also help you to automate your existing solutions with the knowledge. In addition to those, the CATIA technical, we can also CATIA design activities. We can help you on the analysis within the CATIA portfolio with the CATIA analysis module. And also we can look into the system level engineering application where we can actually bring your product details within the system and look at the performance. So as part of the systems level engineering activities, we can also look at some of the code simulations with the physics apps, either with the structural aspects or from the fluid and thermal aspects. So from the structural part, we have experience in a variety of industries providing design analysis and validating that product design and through the testing and optimizing that the product using the simulation products. So the optimization and the reliability, it's another activity that we heavily involve and help our customers. And also we can perform fitness for service assessments, forensic assessments, root cause failure studies. As part of the root cause and the fitness for service, we can look into why the products are failed, and we can simulate FEA-based fracture damage mechanics assessments, as well as SM stress or strain-based fatigue assessment. And when the products are moving when the problems are moving to more multi-physics applications, you may need to do more realistic simulations where you need to actually couple both structural, heats, fluids, or electromagnetic simulations. So that's where we can also help to provide more cost simulations with different physics. In addition to rotor dynamics, structural assessment, the vibration behavior, and also to reduce those the vibration problems. We can help to automate the simulation process and also do the multi-body dynamic simulations. We also have a strong composite simulation capabilities, which can enable the design activities. So around the multi-physics and the CFD, as I mentioned earlier, most of the problems are moving to more multi-physics applications. So we can actually couple either with the structure to fluids, to acoustic to structures, heat transfer to structures, and we can look into more multi-physics problems. And also we can try to optimize the fluid behavior and calculate pressure drops and the flow of regimes in the critical equipment and optimize the design. And we can perform erosion and corrosion studies, combustion simulations, aeroacoustic behavior, and aerodynamics behavior in aerospace application, and hydrodynamics for marine application. And we can bring the heat transfer and thermal analysis and management to our multi-physics application. For digital manufacturing technical expertise, we will be talking today some of the additive manufacturing solutions, but we can provide an assistance with the NC programming. We can look at your manufacturing process and how we can optimize the existing process. Then bring the supply chain management, and also if you are using the robotics, we can bring the robotics engineering, and we can look into the assembly simulations. So I'm going to hand it over the presentation to my colleague Arindam, and he's going to talk about additive manufacturing overview and
thank you, Burak, and thanks, Kanis. This is Arindam here. So, and thank you all for having your time to listen to this webinar. So I'm now gonna talk about the additive manufacturing simulation. So one of the reasons, as Burak said, we picked it up because it kind of shows the application of design solution as well as simulation. So hopefully you will get some idea about how we can help you with your other needs, maybe including, of course, additive manufacturing. So I'll start with a brief introduction to that. Now, I mean, pretty much everybody is talking about additive manufacturing, and there's quite a bit of promise in the recent year. Generally, additive manufacturing, you will see it's so far been used as form, more for form and fit, but now it's also being used as function. So people are making functional components out of additive manufacturing parts. So, and that brings it to the point that we need to better know how the performance of those components will be in actual environment and under different loading conditions. So that's why all this simulation based and design software based analysis is coming into. It's basically we are joining like small parts of materials together under many different processes. So we'll mostly talk about the thermal based process to join material, and it's very similar to welding. And I always talk about this example, like we already live through additive manufacture parts. All our bones are, if you can think of it that way, are actually additive manufactured, and they are also functionally driven design, which I will talk in the context of simulation in a while. But basically what it does is it looks at your load that comes on your bone over the time, and based on that loading profile, it tries to optimize its structure. So the lattice keep on changing so that it has the required strength along the direction of the loading. So your bone may be very weak in a direction perpendicular to the load, but in the direction aligned with the load, it may be very strong. And that's why, like, you will see people who are doing different sports. I mean, they have to do certain exercises because the bone has to be stronger in that direction. So that's kind of a very good example in nature how additive manufacturing works. What are the difference between additive and subtractive manufacturing? Earlier, most of it was with subtractive manufacturing, where we start with a block of material like some kind of ingot and all, and then we will take material out from it and make different shapes based on our component. A couple of limitations on that. So one is you will generate a lot of waste material. And another one was it's very limited to the manufacturing process, how we can cut out material and what we can achieve through the tools. But whereas with additive manufacturing, we start with the material as in a powder form in a very small pieces, right? And then we put energy in the system to combine them and come up with any form or shape. And that brings the point that with additive manufacturing, now your design is limited to what you can think of as the shape. So the manufacturing process does not impose restrictions on what shape you can have for your component. And also the waste will be minimal because you will be using most of the materials and adding them together. So there are with any application, once you go to practicality of the things, and it's a new industry application, so there are the real world challenges, and of course challenges drive innovation. So in additive manufacturing, there are a lot of innovation going on from the material aspect, from the simulation aspect, and also from the design aspect. So here for this particular webinar, we are more concentrating on the simulation and the design aspect. So in a real world, if you want to go from powder to working part, so you start with the raw material, and then you come up with a part geometry and know some idea about the material behavior to come up with the design. And then you will take the design to the field, put it under in-service loading condition, and then your quality of the part, quality of your manufacturing all comes into picture. Now, what is important in additive manufacturing, what you are designing and what you will use at the field, there is kind of an overlap. So a simple example will be during additive manufacturing, you will create residual stresses and distortion. So that also in tandem goes with your how we will be able to apply that in the in-service loading condition for the field. So these are not completely separate parts. So you need to know when you are designing, you need to also know how those will affect, how your design manufacturing effect of your manufacturing process will in turn affect your performance in the field. And that brings in a lot of complexity in doing additive manufacturing parts. And when I say additive manufacturing, again, out of form, fit, and function, this is we are talking more about the functional part. In general, it's a very complex process. There will be many different sub-processes within that. You will have designs, and you will start with the design. You will come up with the manufacturing processes. You will make parts, and then in the field there will be loads, and also there will be a feedback on the part quality. There are a lot of monitoring you can put in. So overall, this is a very complex complex workflow to follow and kind of make it streamlined. So what are the challenges from powder to working parts? So we one is from the design side, you'll have a process planning technology challenges, and then also part quality and yield, and your process now is very closely integrated with your part quality and the yield properties. So you have to have a very tight control on your manufacturing. Whereas in the field, you will be worried about the surface finish, the material defects, and residual stress and distortion. So these are some of the challenges that you need to consider when you are doing the design and simulation of your additive manufacturing parts. Now, as you can see here, you can connect this through many different solutions. Right now in this figure, these are more like separate solutions, which kind of goes into a file-based PLM system. So you will see designer, simulation, optimization, and there is the actual printing and also testing of it, and then scanning and measuring because of the distortion and surface finish and material defects. So this can take from weeks to months. And now how can we bring this process from days to weeks? So now connecting them through a more collaborative environment, we can, because then effect of changing one segment, one sub process within that will also be connected with the other sub processes. So what will happen is you will have a better change management, and also you will have the change at one place will trigger action at other places. So you will have a better control of your design. Now, one of the key aspects for additive manufacturing, as I'm emphasizing again and again, is the simulation. Now, simulation can be more heuristic, but if you can make it more physics-based, then you are doing a more realistic simulation, because at the core of every natural process, there are certain physics that is happening. So you want to bring those physics to your modeling or simulation capabilities. So in additive manufacturing, it's even more important because the processes are really complicated, and sometimes heuristic approach like eigenstrains and all, they really doesn't work. They cannot bring out the problems that you might have. So what kind of process you can look at? So for you would do some sort of optimization problem. So again, instead of experience-based or heuristic optimization, you can do more mathematics-based optimization. You can work with the calibrating the material, of course, simulating the stress and distortion. So stress strain field, you will get the displacement field, and from that you will get the stress strain field. So what are some of the challenges again for simulation that it has to capture is you will have cracking in additive manufacturing parts. You need to know how the parts are going to behave under certain loading if they have cracking. So there will be tolerance problem. So that can also have an effect on your functionality of the part. And of course, you can do trial and error runs, do experiments. But if you have a simulation framework, you can do more of a physics-based numerical trial and error, which will significantly reduce the time as well as the cost. One of the things when we talk about simulation or for any processes, if you look at metal manufacturing process currently available, so there are very strict codes and guidelines available. So if I'm buying a certain grade of steel, I'm pretty much sure that I'm going to get this and this property. And the code specifically state those numbers. They are called code minimum numbers. So because there have been a lot of tests, the process is pretty well defined now. So we are confident that if I buy this steel, my yield strength minimum yield strength will be this. Additive manufacturing, we are not there yet. There is a lot of innovation, a lot of new applications are coming in. So there is always a need for more and more standardization and validation. So from design aspect, materials, process, and performance, there's a validation effort that's going on. ASTM, NIST, ISO, and also many manufacturing organizations, they are coming up with a standardized process. So now let's talk about the function-driven generative design. So generative design is the form of finding the process that can mimic nature's evolutionary approach. So what I have told about that bone growth in animals. So that's kind of a very good example for generative design. So we want to bring that similar concept into our engineering arts. So it can start with the design goals and then explore the many possibilities with the permutation combination of that to find the best solution. So it unifies modeling, simulation, and optimization in a single environment. So you will do an effective product engineering. So you will remove the bottlenecks that makes it very cost prohibitive. So and then the workflow is generally very intuitive. So designers with non-expert solutions, they can easily work around with the workflow. So one of the reasons for additive manufacturing, one of the focus for additive manufacturing simulation development by Dassault Systèmes is make it very intuitive. So you don't know, so a designer can concentrate on the design and doesn't have to worry about what exactly is going on with the simulation modeling, but rather should be able to give the parameters, and then the simulation modeler should be able to take care of all the details. Everything is automated, so functional driven conceptual shapes and detailed organic shapes, all this comes automated. So there are algorithms that works behind the process, and it will take care of that. And also the seamless collaboration with designers, simulation, and manufacturing engineers. So this is the collaboration and automation that can bring that complex process from months to weeks, from weeks to days. So in the new design paradigm, what we are looking at is first we'll capture the functional specification. From there, we will go into generate and validate conceptual shapes. So first you need to have some sort of validation with your shape, and then you can look at the concept trade-off. So there are always, you will need to give up something to get something, and it will in a very well structured mathematical way, it will do the trade-off analysis and find the best concept based, of course, the KPI will be defined by the users, but it also gives what are the possible KPIs that you can define. And then once you generate the shape then you will do the modeling and validation of that. We always remember there has to be a strong validation in all these aspects. So because simulation, there are too many parameters, there are a lot of assumptions. So first time when you start the process, when you set up a workflow, validation is the key. So one need to have some sort of validation for their simulation model. Once it's validated, then you know the physics is properly captured. Now you work with a different design, then it's not gonna change much. So behind the scene, what is happening? So there is a topology optimization Then also there is a constraint based optimization problem. So it looks at the constraint for mass, symmetry, stress and displacement, and also there is a geometry validation. So you will look at the surface distortions and all this, and you will set your own criteria for that validation. So one thing I forgot to mention. So all this thing with the Dassault system solution, it can be used within the CATIA solution. So on behind the scene, it goes with CATIA is the one which drives all these efforts. And now we'll go on to, once you validate your conceptual design, now we'll look into manufacturing planning and manufacturing planning and the definition. So what we are doing here, process is the key. So additive manufacturing, it is extremely important to know the process. If you think of it, this is like, I mean, when you're talking about metal additive manufacturing with some heat or a laser beam out there. So what you are doing, basically, you're doing many micro weldings. So then your process, how is the speed of your laser beam? What is the path? And layer to layer, what is the time difference? And how you are, what kind of materials you are mixing? So all those things are key, and how your supports are. So based on that, your final properties of the manufactured part can vary quite a bit. And also, as we talked about, cracking and all, distortion and residual stress issues that can play significant. So manufacturing can play a significant role into that. And depending on your need, you have to minimize that. So it's good to understand this manufacturing process well. So now so we have the design covered, we have the process covered. Now we're coming to the virtual printing simulation. So Simulia is used for the virtual printing simulation. You probably have heard about the FEA solver Abacus. So Abacus is behind the simulation, but it has been enhanced. I have one brief slides on some of the enhancement that Abacus has to more capture additive manufacture simulation process. So now it will be a guided simulation assistant. For this example is for powder bed fusion process, but it can be for any other process as well. So guided simulation assistant is the key here. So again, as this might be more of a designer's domain. So if they wanna do simulation, it should not be scary for them. They should not get into the details, but they should understand what needs to be simulated, what the simulation results are telling us, and how to read that result, but not get into the details of making of the model. So is this automation, this guided process is very important. Here, some notes on the simulation framework. So this is there are a lot of changes. If you can think, there are a lot of changes happening from material aspect. This is the thermomechanical process. So we have liquefaction and then solidification happening, and this is so when you go through the scanning path. So there are, as I said, these are sort of like a micro welding. So there are too many times you have to do the weld process. So if you look from every mesh capturing one time point on the laser path, that's not very efficient. So because your model will have, depending of course on your size of your design or component, your model will have too many meshes. So it will be very expensive to handle that in a timely manner, and also in a cost-effective way from simulation resource point of view. So therefore, there has been a lot of enhancement that has been put into this. So one is partial element activation. So now basically your mesh is sort of like a background mesh. So within that, it doesn't have to follow exactly your interest in time and space. So, and also another thing is you can do more of an adaptive simulation. So what you can do is initially you run your design with certain coarse mesh, and you kind of find out that where my high stress regions are, where my large distortions are, and then within that area you can refine your model. Just within those areas you can have a finer mesh to capture the gradient more accurately. But as I mentioned, due to partial element activation, your mesh doesn't have to exactly follow your time point of interest and your spatial domain that you are interested in. So you can really have relatively coarser mesh, but within one model you can have finer mesh at some point and coarser mesh at another point. So this will bring down the total computational time significantly, and also this entire process is automated. So all you have to do is designate certain areas, put some parameters for simulation, and all the modeling aspect, all the meshing, everything is done automatically. So there are trade-offs, trade-off studies, so about performance versus accuracy, right? In any design, one of the thing is you can put all your computing resources, but then maybe your problem size will get too big. And so every engineer, every designer, every simulation engineer has to look at what amount of computing effort, what amount of computing resources I'm putting to solve a problem, and what is my end goal. Now, for example, here there are certain, I mean, these are just different examples that you can see. So actually, if you look at the physical print part, so it's the probably at least for the first two examples is the most time consuming part. So your design and production that might have to be very quick. So now if you do a very detailed simulation, you may not you will achieve the accuracy, but you may not achieving the accuracy within the stipulated. So now we have to be smarter. So for the design, what we need to do, we need to look at what problem we are solving, what are our interest regions, and then be flexible on the accuracy of the problem. So what Simulia provides with the solution is you can pick and choose your accuracy, your level of details, your physics, what kind of, I mean, you sometimes you may not want to bring all the physics, maybe some averaging technique is good enough. So all these aspects are there. And this is an engineering decision that a designer or a simulation engineer both should be capable of making, because this is not getting into the core modeling aspects of FEA. This is more like looking at from what I'm going to use the results for, and what is my component is for, and combining those two knowledges together. So post-processing. So one is you set up the model, you run it, and it all, of course, it will solve for displacement. From displacement, you will get stress and strain. But what finally I'm looking into, and also thermal is another process. Thermal is another output of interest. So post-processing is extremely important. So in the post-processing environment, you can look at the stresses after the heat treatment. So you can do a heat treatment analysis. So you make the part, additive manufactured functional part, and then you can simulate it through a heat treatment process. Sometimes because additive manufacturing parts will have voids, and to reduce the void, there are high pressure heat treatment, high pressure heat treatment under high pressure, and also sometimes you want to reduce the residual stresses, so you heat treat your component. So all these things you can as a part of post processing, you can take that manufacturing part and do a post processing to get those other post manufacturing effects. And this will give you an idea about when you are going from printing to actually putting that component in real life environment. You can simulate the entire process in that. Now, in-service capability also. Now, one of the questions one may ask, okay, I have this additive manufacturing component. I know the yield stress. I know maybe the hardness. And now, how am I gonna know how well the part is performing in real life? Now, so I have some nice videos here. So in the middle one, you can see there is a nozzle which initiates a small crack, and then the crack grows under the given service loads. Now, I mean, this example particularly is not for an additive manufactured component. This is more of a vessel with a nozzle connection. But you can imagine you can get an additive manufactured component. Simulation has given you all the residual stresses, all the distortions, all the material properties of interest, which is mostly yield and hardness in this regard. Now I can do a crack growth analysis into that and put the component under service load and see how the crack is propagating under the given loading condition. Because
I mean, depending on how your loads are, crack tends to propagate in the maximum loading direction. In the tensile, maximum tensile loading direction. So your crack, if you have a complex loading, complex geometry, which for most of your additive manufactured part will have, then it's not very easy to predict the crack growth. So this simulations capability will accurately predict that crack growth. Now, looking at the crack growth, one can come up with the remaining life or come up with how many cycles of thermal or pressure loading I can subject this component to. What will be my maximum load? Will my crack be stable under the maximum load? So all this information can be obtained. And also from the effect of residual stress. So what residual stress that does, if you have a component with and without residual stress, you will see that the fatigue life are different for those. So bringing in residual stress is extremely important if your concern is of fatigue life. And also to initiate the crack, residual stresses may or may not help initiating a crack. So residual stress is self-equilibrating. So through the thickness, residual stress, the total force coming from the residual stress will be zero. So if you look at through the thickness, there will be tensile residual stress and compressive residual stress. So if you have a micro crack at the tensile region, then most likely it will grow into a dominating crack. So these are some of the things that you will have a closer look at, because now you have the simulation. It helps you look into the physics of the problem that went through the manufacturing process into a very finer level of detail. So by joining all this, so joining your manufacturing, joining your post-processing, joining your in-service capability, you can get a total picture of starting from the powder, how do I use this component in real life. Again, validation is extremely important, and one of the aspects is also doing the optimization. So even for this, for this kind of solution, there are validation aspects of it. Now, one of the thing to note here is the material coverage. So material here is extremely important, and when you work with a steel, you already know the properties of, say, yield and Young's model. So you put those properties in your FEA, and you use those numbers for your FEA simulation. Here, the material properties are in effect. Your manufacturing process largely changes how your material is going to behave in the additive manufacturing. So there is always a need for microscale evaluation and look at the material performance. So from the microscale, what we can do from simulation aspect, we can look at the material properties via finite element homogenization technique, and also there is a representative volume element based micromechanics simulation. So all this can be bring into to obtain from the microscale properties to the macroscale properties. So material evaluation during print. So during print, you have to look at how materials are changing under temperature, and also due to the thermal process, the grain nucleation and growth, all the metallurgical transformation, all these things are happening. So your hardness will change. So your thermal stress, thermal field has to be accurately captured to come up with the material hardness in your manufacturing part. And then finally, the performance. So once you make the material, you put it in situ, and then there's fatigue life, there is a corrosion effect, there are fractures. So all these things can be modeled. So simulation validation. So now, I mean, anybody probably can come up with the software and say, okay, I have done this, I have done that. But unless you really verify, it really doesn't. I mean, nobody will be confident enough to use that, right? So Simulia has done a very extensive test with many national labs and also additive manufacturing centers. Look into both the thermal properties in their additive manufacturing simulation and comparing with the actual test that has been done, and also with the hardness and strength properties, and looking at the residual stress, looking at measuring the distortion. And in most of the cases, they have found very close match. Sometimes if there is some noise that's more coming from, because in any actual manufacturing process, there will be some noise in it because of the variability in all the processes and the parameters. And if you do more of a statistical analysis, so you can come up within the simulation, you can come up with a band, and generally you will see that the variation from the test
is fitting within that band. So all this detailed validation work has been done. So verification has been done to make sure all the modeling, all the physics are put properly, and the FEA model is robust enough to capture those, but then the validation is done whether it actually matches with the test data. So here are some examples of residual stresses and melt pool and microstructure. So these are actual examples. There are references available for that, and this has been presented in international conferences and in open literature. So if you have interest, you can always refer back to them. So what are the goals for physics-based process simulation? One of the things is you might want to do a process parameter analytics as one of the key aspect is looking into the process parameters, how they are changing changing your performance of the part. So the tools are equipped to do a process parameter analytics. So you can do a design exploration or optimization based on the process parameter. So in summary, what we are looking here is the task is functional driven design, which is done through CATIA, which is a Dassault System simulation and Dassault System solution. And then we are doing the manufacturing process planning, which is done using Delmia. So there's the example we talked about is powder bed, but there are other examples as well. And then the manufacturing process simulation, which is done using Simulia. So CATIA, Delmia, Simulia are covering the entire workflow for additive manufacturing process. And then finally, you want to do virtual testing, and all that can be done through optimization, which is inbuilt into the 3D Experience platform, and then you will look at your process parameter optimization. So having said that, I'm pretty much, I have covered all the slides that I have, and if you have any question, please let me know. I do see there are some questions over there. Okay, so the first question is, are the meshing techniques any different for a printed part? So the meshing technique in general is not very different, but the meshing algorithm, they are using an enhanced meshing algorithm, which if you go into Abacus, the underlying there is a meshing algorithm. So that has been improved from how you will mesh an arbitrary geometry. But other than that, the meshing techniques are overall similar. And another thing is the user doesn't have to worry about the mesh anymore. So given the geometry, the mesh will be automatically done in an efficient manner by the software. Which materials? So they have tested on carbon steel extensively. I think stainless steel, there is 1 or 2 validation cases, but right now both the carbon and stainless steel, they have been tested for the metallurgical properties. Okay, so I'm still waiting if there is any other questions, and let us know how we can help you with your needs. And if there is any follow-up conversation you want to have, we'll be more than happy to talk with you. And our contacts and everything are there with the slides, and you should also have seen emails from us. So feel free to contact us through any means, and we'll be more than happy to have a discussion with you. Okay, so I'll wait for a few more minutes if there is further questions. Okay, so yeah, looks like there's no further question. So we'll wrap up the webinar for today, and looking forward to work with you all closely. And thanks for your time for listening to the webinar. Thank you all.